Okay, I got the thumbs up. Well, thank you, Steve, for the introduction.
I think we're good to go.
Thank you
Audio
all for being
sounds
here
decent
today.
now.
It's a real pleasure for me, working up on Mount Hopkins that you guys see every day, to come here and tell you a little bit about the telescope that's at the summit there. So this talk today is going to be really more technically oriented than science oriented. I'm going to tell you a lot about the observatory, the technical innovations that went into the observatory, and how we operate the observatory, more so than the science, but I'm certainly happy to take questions about the science that we do also. So the background of my opening slide here is a beautiful image of UGC 1378 that was taken with the telescope at the summit, the MMT, with an instrument that we call Binospec, one of our big workhorse instruments. So I thought I'd start off with a nice pretty picture to set the stage for how we get images like this. Yeah, this is a good one, but it's going to stop. This is a good one.
It's okay. I'm the hero. Okay.
Yep. Well, you're advancing for me. Okay. I don't have control anymore. So I'm going to start off talking a little bit about Mount Hopkins. You all see it here from Green Valley, quite easy. Next slide, please. Here's a nice image of Mount Hopkins taken from the corner of Elephant Head Road and Mount Hopkins Road. I like this picture because it sort of points right to where the telescope there is at the summit. Mount Hopkins is about 40 miles from Tucson as the crow flies directly, but it takes much longer to get there. It's at the summit's at 8,550 feet. Sorry.
You should be able to do that. Will you try one time for me? Okay, will you advance for him for a second?
Which one are we doing?
Right button.
Okay.
Yeah, Amy took my joke. I was going to say we can operate big telescopes, but this technology stuff is really hard. Here's another beautiful image of the MMT at the summit. Here with Comet Hale-Bopp in 1997. This is quite a while ago, 27 years ago, but the observatory has been operating much longer than that. Yeah, next slide, please. We're now in the 46th year of operating the MMT at the summit of Mount Hopkins. Next slide. MMT started operation in 1979, as you can see over here, 1979, still operating today. And this is an aspiring director for the observatory back in 1979 when it got dedicated. I was 9 years old at the time, but I'm happy to say that having now worked at the MMT for 22 and a half years, I've almost been there for half of the lifetime of the observatory. So although I was young when it started, I've been there for quite a while now. Next slide. This is one of my favorite road signs ever. Caution, telescopes in operation. You know, if you're driving down the road, you have to be very careful because these telescopes might jump out from the side of the road in front of the car. But many of you know, next slide, that sign is there to protect these telescopes, which are at the Fred Lawrence Whipple Observatory base camp. If you attended last month's lecture, you heard Wystan Benbow talk about the Veritas array, these 4 telescopes that are located at base camp. They have very sensitive detectors, and because of that, we don't want cars with bright lights shining on them because it could damage the detectors. Next slide. There's maybe other reasons for this caution sign. We also have other things to be cautious of. Next slide. For example, we have a lot of wildlife up there on the mountain. This is a picture that was taken in 2022, in October 2022, up near the summit. This is just below the summit. We have a common building over here, and one of the observers had driven up, and then this wildlife camera got a snapshot of a bear getting very curious about the vehicle there. We get all sorts of wildlife, ring-tailed cats, mice, obviously, bobcats, mountain lions, which is one I haven't seen yet, but a lot of people have. Next slide. The other thing that we're worried about, we have to be cautious about, are forest fires. We've been very lucky on Mount Hopkins. There haven't been any recent forest fires up there, but there was a fire called the Florida Fire in 2005, which burned most of Mount Wrightson in the Santa Rita Mountains. I was at the mountain that I had been observing the night before. I got up the next day and I saw this stream of smoke coming up on the other side of the ridge from Mount Wrightson there. And this is in July of 2005. And then about a week later, next slide, that had really escalated and burned most of Mount Wrightson. And so here you can see an image from the summit of Mount Hopkins looking down into Madera Canyon here. And the fire has progressed down into Madera Canyon. Firefighters here, you can see the red slurry that was poured around the summit of Mount Hopkins to protect the observatory. Fortunately, this was July 16th. July 16th, that's usually, the monsoon is about to start then, and it did. The firefighters kept it at bay for a while, and then the monsoon came in and helped put out the fire before it rushed back up Mount Hopkins. Next slide. Here's another image of the summit taken from a drone now, showing the observatory from above. One thing you'll notice from this picture is, the telescope sits at a very small footprint on the top of the mountain there. You can see the road going up. It's a 20-kilometer road, not a 12-mile road. One of the advantages of Mount Hopkins is that it's a very sharply peaked mountain. The mountain falls off very quickly on all sides, and that makes it a very good site for doing astronomy. What we want to have is laminar flow going over the telescope. We don't want turbulence that'll affect the image quality. Mount Hopkins is an ideal mountain for having good image quality because very sharply peaked mountain, and the prevailing wind comes from the southwest where there are no other mountains for the turbulence to generate over. This is the area down here is the dorm area here. Then there's a common building. That's where the picture of the bear was taken, right there at the common building. Next slide. Now here's an image looking down the mountain from the MMT. So the structure you see in the foreground here, this is actually the MMT telescope. And you're looking down to the southeast to the telescopes that are down on the ridge, the rest of the Whipple Observatory telescopes. Next slide. And here is an unobstructed image of the ridge from the summit. There's multiple telescopes down here on the ridge. You guys can see the MMT from here in Green Valley, but these telescopes are hidden because they're on the backside of the mountain relative to Green Valley. There's a number of different telescopes there, a lot of them doing exoplanet science now, but a lot of history doing a lot of other science on the ridge. Next slide. Now I'm going to tell you a little bit about the origins of what we call now as the MMT. It's really an acronym for the Multiple Mirror Telescope. And when I show you the next few slides, you'll understand why it was called the Multiple Mirror Telescope. Next slide. This is an image of the original telescope that was in that building that's at the summit there. So this telescope, called the Multiple Mirror Telescope, had 6 1.8 meter mirrors on a common mount. So you can see the individual mirrors here. Here's 1, 2, 3, 4, 5, 6. The total collecting area of those 6 1.8 meter mirrors was equivalent to a telescope that was 4.5 meters in diameter. So the time that the MMT was dedicated in 1979, it was the 3rd largest telescope in the world in terms of collecting area. And this telescope operated from 1979 to 1998. Now the new telescope has operated actually longer than this old telescope. Next slide. The origins of the Multiple Mirror Telescope really started in a space project. This space project called the Manned Orbiting Laboratory. This is a depiction of it. It was an Air Force project that ran from 1963 to 1969. You can see that the bottom part of this spacecraft is open here, and I'll show you why in a minute. Next slide. This is a kind of a drawing from that manned orbiting laboratory showing the different parts of the laboratory. Up here in the front, you have seats for pilot and the co-pilot. There's a habitable zone in the middle there, and a tunnel, airlock tunnel that goes in between the two. And then on the back side here is this mission module. You can see the relative size of the spacecraft relative to a human there. Next slide. So this is, not only is it the mission module, but it says spy telescope there, right? So if you look back here, there's a mirror back here, and this mirror is actually looking down at the ground. Next slide. This is the optical light path for that telescope. Light comes in from the ground, looking at what's on the ground, gets reflected off of this fold mirror here, goes back to this mirror, which starts focusing the light down off of these two fold mirrors onto a camera here. So this mirror right here was a 1.8 meter mirror. And so there were multiple of these mirrors made for this project, but the project was canceled. Next slide. Now this is a slide we're not going to be able to hear. So I'm just going to describe what, this is Aidan Minell. He's, maybe you can start this slide, Steve, and I'll just describe what he's saying. This is Aidan Minell. He was a faculty member in the optical sciences at the University of Arizona, and Aidan was familiar with that manned orbiting laboratory project, and he was familiar with those 6 1.8 meter mirrors that were supposed to go into that project. When the project got canceled, he contacted the Air Force and said, hey, are you going to use those mirrors? Because I've got an idea how we can use them. And he came up with a design for a multiple mirror telescope, putting the 6 1.8 meter mirrors on a common mount to produce the equivalent of a 4.5 meter telescope. Next slide. How did that work? Well, each one of the mirrors in the multiple mirror telescope, here just showing 2 of them, but as I said, there's 6. This just shows you the way that the light travels to get into the telescope. Each one of the individual mirrors acts like an individual telescope, but the light from each one of the 6 telescopes is combined and sent to a common instrument behind the telescope. So here's the light path with these arrows. So the light comes in from your astronomical source, bounces off the primary mirror, which starts to focus it, goes up to a secondary mirror here, back down to this fold mirror, and then off of a beam combiner into the instrument behind the telescope. The same thing's happening with this mirror and the other 4 mirrors as well. So the images all come into a common point, at which point you have your detector or your science instrument allowing you to combine the light from all of those telescopes. There was also a guide telescope in the center there. And if you get the chance to come to the summit of Mount Hopkins, we have a display case up there where this unique optic, the beam combiner, is actually in our display case up there. Next slide. One of the unique things about the MMT was that they wanted to try to keep the cost down for the original observatory. And one way to do that is to keep the enclosure cost low. The way that telescopes have been built in the past, they've been built as equatorial telescopes, shown here like this says the 5 meter Palomar Hale telescope, but most people know it as the 200-inch. This telescope has one of its axes pointing at the North Star up here, and then it just tracks in the other axis. That's called an equatorial telescope. But in order to have a telescope that big, be able to move around inside of a dome, you need a very massive dome so that the telescope can move around without running into the dome at all. That's similar to the design for the 4 meter telescope up on Cape Peak, the Mayall telescope. You can see how large this structure is, not only the dome itself, but just the building to put the telescope at the top of it there. This is the multiple mirror telescope in comparison, much, much smaller. And what you can see from that is, first of all, it's not an equatorial telescope. One of the axes is not pointed at the North Star. It's an alt-az telescope. So the telescope moves up and down in elevation and spins around in azimuth. It was one of the first large telescopes to operate that way. Now all modern telescopes operate that way. But the other problem is you can see that if you tried to swing the telescope around inside that building, it wouldn't work. It'd run into the walls and whatnot. So the decision was made to make the building, the entire building, rotate with the telescope. So you can see there's little wheels down here at the base. That allows the building to rotate around as the telescope's moving around. So we command the telescope to move and the building just follows it around. That allowed us to keep the structure relatively small and keep the expenses down. Next slide. So this is the image of the multiple mirror telescope, as I said, was commissioned in 1998. Next slide. And then this is the telescope as it exists today. So you can see no longer is there a multiple mirror telescope in there. There's a single 6.5 meter mirror in the same building as that multiple mirror telescope. In fact, if you saw the previous slide, this blue structure right here called the yoke, which holds up the telescope, that's the same structure as the same yoke that was used in the multiple mirror telescope. And one thing I like to say is that when there was a decision made to convert the multiple mirror telescope over to a single primary mirror, they had to make a decision how big they wanted to make that primary mirror. And that was set by how big this yoke was. They could fit a 6.5 meter mirror in between that yoke. And so that set a standard for modern telescopes. Now there's several telescopes that are 6.5 meters in diameter, including one you may have heard a lot about recently, the James Webb Space Telescope, 6.5 meters in diameter. So James Webb, the size of it is based on the original multiple mirror telescope. Next slide. So I'm going to tell you a little bit about the mirror now. Next slide. The idea of converting to a single 6.5 meter mirror came about because of advances that were happening at the Stewart Observatory Mirror Lab, which is now called the Richard F. Karras Mirror Lab. Roger Angel and his crew had determined how to make very large mirrors very lightweight. One of the things I didn't mention about when you saw that video of A.D. Meinel, he mentions in the video that the mirrors that were used in the original multiple mirror telescope were very lightweight. And they were lightweight because they were going into space. They needed to launch them, so they needed to keep them lightweight. And so they used the mechanism of basically having a very thin front plate, a very thin back plate, and a structure in between the two, which helped keep the mirrors fit. And that's also what Roger Angel uses to make these large mirrors at the Mirror Lab. The process is that you fill a large mold with these ceramic hex cores, and then on top of that mold, you load chunks of very pristine glass, and then on top of that, you put a cover over the top of it, and that's a furnace now. So you heat it up, and that causes that glass to melt and flow into the mold. And one of the unique things about the Mirror Lab is not only are you heating it up and melting the glass, but you're rotating it. In this case, at 7.4 rotations per minute. So that structure is rotating while the glass is melting. And the advantage of that is that that creates a parabola in the glass structure. And so you have to do a lot less grinding and polishing to make a good mirror. Once the mirror starts to cool down and it solidifies, then they stop rotating the furnace, but it takes several months to continue to cool that mirror slowly over time as it anneals. Next slide. When you're done, you pull this out of the mold. So this is the actual 6.5 meter mirror that's up there on Mount Hopkins now. It was cast on April 29th, 1992. When this mirror was cast on that date, it was the largest mirror that had ever been cast. That didn't hold for very long. Nowadays we have big 8-meter class mirrors, and so, but for a short time, the MMT was the largest astronomical mirror that had ever been made. It weighs 10.5 tons. In this picture, you can see that these white structure behind the mirror there are those ceramic hex cores, which will actually get blasted out with water in the end to just leave nothing but glass left in the mirror. Next slide. I like to show this just to give people a scale for that mirror. You've seen it with people in it, so you sort of get the feel, but I tell people the mirror's diameter is approximately the distance from a basketball hoop to the three-point line in college. Next slide. Here's another image showing the scale of the mirror. Here we have the MMT staff and a visitor, I guess. This is the 6.5 meter mirror here, and overlaid on top of that are the sizes of the original 1.8 meter mirrors from the original multiple mirror telescope. The other thing that this image shows are these green things which are in the back of the mirror. So this is sort of looking at the back of the mirror. These green things here are actuators that help us lift up the mirror into its operating position while we're observing at night. I'm going to tell you a little bit about those in a minute. There's 104 of them on the back of the primary mirror. Next slide. So here's a cutaway of the primary mirror. I said that, you know, in order to lightweight the mirror, you want to make it mostly hollow, and that's what it is. There's a front plate on the primary mirror that's a little over 1 inch thick, a back plate that's a little over 1 inch thick, and then this honeycomb structure in between. You can see that there's ribs in there, but in between the ribs, it's all hollow. That keeps the mirror relatively lightweight. When that 200-inch telescope on Palomar was cast in the 1940s, it was thought to be the largest mirror that could ever be cast because it would the mirrors just get too heavy to actually put into a structure to be able to move them around. But in modern technology, we can make them lightweight, and then we can make structures that can move them around and point to astronomical sources. Next slide. There's another rendition of the mirror just cut away, so you can see a slice through the mirror here. There's a cell around the mirror. Here's the mirror itself, and then behind the mirror and the back of the cell, there are those actuators that help pick up the mirror to operate every night. Next slide. Here's an image of an actuator. This is actually upside down. How it looks in the telescope is there's 2 cylinders of the actuator, one that points up toward the zenith, and another one that's at 45 degrees to that. And we need, well, I said that these actuators actually lift the mirror up a little bit in order to observe during the night. But we actually need 2 of them because we move the telescope, right? We tip it down. Next slide. So during the night, we tip the telescope down to observe whatever we're observing, and then the load from the actuators moves from this cylinder to this cylinder to help keep it elevated and in position where we need it for observing. Next slide. So after the mirror was cast, it was brought up the mountain and put into the new telescope. You can see the telescope is now in the building. Here's the mirror being lifted up and brought into the building now. Mirrors do not have lifting points on them, so you can't hook up hooks to pick up the mirror and lift it into the dome. So the way that this is done is with vacuum chucks. You actually use vacuum to suck up on the front of the mirror and lift it up with the crane and bring it in. So this is an area where you really want to trust physics. Vacuums work. Next slide. Now I'll talk a little bit more about the telescope. Next slide. So this is a drawing of the telescope pointing now at horizon. So normally we'd be pointing up the zenith, but just to demonstrate the layout of the optical layout of the telescope. This is the primary here on the left, primary mirror. We then bounce the light off a secondary mirror, and with the MMT, we actually have 3 different secondary mirrors we can use, one at a time. We don't use them all at once, we just use one at a time. The secondary mirrors are labeled by their final focal ratio of the mirror, so f5, f9, and f15. Why do we have 3 different secondary mirrors? This f9 secondary actually produces a beam into the instrument that's the same focal ratio as the old telescope. So the idea was that on day 1, as soon as we got the telescope working, we could mount the instruments from the old telescope on the back of the new telescope and start doing science right on day 1. So that's what the F9 secondary is for. The F5 secondary is very unique too. It works in conjunction with a couple of other optics which are here. This is called the wide field corrector. What that does is it allows us to get very good image quality over a very wide field of view. And I'm going to show some pictures of that in a minute. So that's why we have an F5 secondary, so we have a very good image quality over a large field of view. And then I'll tell you more about the F15 secondary in a bit. That secondary is a very unique secondary too, one of the first of its kind. And just for those that are interested, we have a classical Cassegrain design, so it's a parabolic primary, hyperbolic secondary, and there's 3 different configurations. Next slide. Oh, I also wanted to point out that the secondary mirror, this F5 secondary mirror, the diameter is 1.7 meters in diameter, so that's almost as big as the original mirrors for the multiple mirror telescope. So that's a really big optic. This wide field corrector that sits here in the center hole of the primary, this is a drawing of it cut away. You can see there's 3 different lenses in there, very curved lenses that give us that really, really good image quality over a large field of view. Next slide. Here's an actual image of that wide field corrector. You can see the glass here, very, very curved lens. And I guess there's not really scale here, but it's a few feet in diameter. Next slide. And when we mount it in the telescope, you saw it's in the central hole of the primary mirror. This is kind of a hard image to interpret, but this circle here is the central hole of the primary mirror. The mirror is actually reflecting the inside of the dome and the sky here during the day. And then you can see this optic is that wide field corrector sitting in the center hole of the primary. Next slide. So, as I mentioned, that combination of that big F5 secondary and the wide field corrector allow us to take images that are like this. This is an image of the galaxy M33, taken with an instrument that we don't actually have anymore called MegaCam, but it allowed us to get really, really good image quality over a large field of view. This is my favorite image taken with the MMT. M33 is one of my favorite galaxies, but it's amazing. This screen doesn't do it justice. If you have it on your computer screen, you can zoom in. You can look into, individual star clusters here and pick out individual stars in that galaxy. It's really beautiful. Next slide. I'm not going to talk much about this. I just wanted to point out that MMT is very versatile. We have several instruments that can mount on the back side of the telescope, and this is listing some of those instruments. What I've shown here is the wavelength that the instrument works in. Over here is the optical wavelengths. In the center here is the near-infrared wavelengths, and then off to the right is the mid-infrared wavelengths. And then this is just showing the field of view, how big the field of view of the individual instruments are. So you can see that there's multiple instruments here that can mount on the back of the telescope. You can go to the next slide. That was for imaging capabilities, but mostly what we do at the MMT is not imaging, but spectroscopy. So this also lists our spectroscopic instruments. Spectroscopy is where we take the light from our astronomical source, we disperse it so that it comes out in its rainbow colors. We measure the intensity of the light as a function of its wavelength. So how much we disperse it is shown on this axis here. The more dispersion, the more individual pixels we can get in each wavelength of light goes up in this direction. And again, this is a wavelength direction here. So you see a number of different instruments in different configurations that we can use at the MMT. And really all I wanted to do by showing you those couple of slides is demonstrate that with our 3 different secondary mirrors in our suite of instruments we have there, the telescope is very powerful for doing a very wide range of astronomical science, ranging from people who are studying objects in our own solar system, to studying stars in our own galaxy, to studying nearby galaxies like M33 that you just saw, to studying things that are more distant, even the most distant objects in the universe. So really the science that's done at the MMT, because it's so versatile, it really runs the gamut of all astronomical science. Next slide. So now I'm going to tell you about that F15 secondary. I talked a little bit about the F9 and the F5. Now I want to go on to that F15 because it's a very unique secondary mirror. Next slide. That's this, just as a reminder, that's this smaller mirror here. It's 64 centimeters in diameter. Next slide. And here's an image of the mirror. Sort of looks like a normal mirror, but there's some unique things about it. The first thing you'll probably notice, it's got a bunch of polka dots all over the surface of it there, right? Well, that's actually not polka dots on the surface. I'll show you what that is in the next slide. What it is the back side of this mirror is actually coated in aluminum. That's why you're seeing reflection. But in certain spots on the back side of the mirror, there are little magnets glued on there. And that's what each one of these polka dots are, magnets on the back side of the mirror. When you look at this mirror, it looks like it's a pretty thick mirror. But really, the mirror is actually about the thickness of my laser pointer there. It's only 1.8 millimeters thick. The rest of this structure is just support structure for the stuff that goes behind the mirror. Next slide. So if you look at just the mirror itself, just the piece of glass, this is an image of it here with no aluminum on it. So you can see the piece of glass here. You can see how big it is in diameter, 64 centimeters, but only 1.8 millimeters thick. That's about the thickness of a nickel. And this mirror is like a big contact lens. That's one way to think of it. Very, very, very big in diameter, very, very thin. And you can see that on the back of these mirrors, each one of these little circles is a magnet that's glued on the back of the mirror. Next slide. And behind that, you saw that there was more glass structure. This is actually what's called a reference body that sits behind that mirror. And in this reference body are 336 holes that match the positions of those 336 magnets on the front of the mirror. Next slide. And in each one of those holes is one of these. This is what's called a voice coil actuator. The voice coil actuator uses electricity to produce a magnetic field which can push and pull on a magnet. Same way, maybe if you have some nice speakers at home, same way the speakers work, pushing and pulling on the magnet to produce the sound that you hear. These voice coil actuators can push and pull. There's 336 of them on each of those 336 magnets that are glued on the back of the secondary mirror. What that allows us to do is to change the shape of that mirror very fast, at potentially 1,000 times every second. We can change the shape of the mirror. And the reason we do that is we want to take out the effects of the Earth's atmosphere. When starlight's coming through the Earth's atmosphere, it's getting distorted by the Earth's atmosphere. And we can measure that distortion, change the shape of the mirror, take the distortion out, and give us a pristine image quality as if we were flying in space. Next slide. And this is a demonstration of how that works. Here's the mirror mounted on the MMT here. This is showing an image of a star before we turn on that system. And then when we turn on the system, you can see how much sharper the star gets over here. And you can even make out that there was actually a fainter star here, but not just one, there's actually two stars there. And this kind of shows it in 2 dimensions here. You can see there's the original blurred out star and its companion. And when we turn the system on, it gets much, much sharper, and we can make out the 2 stars that are its companion there. So very powerful capability for being able to take away the effects of the Earth's atmosphere. The MMT had the first adaptive secondary mirror ever. It was commissioned around 2002, and it's still operating today. And now most of the big telescopes that you hear about being built are now adopting this technology for their own use. Next slide. The last thing I want to touch on is just the coating for the primary mirror. I'm going to take a quick pause to get a drink here. Okay, next slide. You saw the way that the mirror was made. What we need to do is we need to take that piece of glass and we need to coat it with an aluminum coating in order to make it reflective. Here you can see the telescope, and you can see the primary mirror here, and you can see that it's reflecting light because there's already aluminum on the surface. That aluminum over time will degrade. And so we have to take measures to keep it from degrading. It oxidizes very quickly, becomes aluminum oxide, and that causes it to tarnish, so it doesn't have the same reflectivity as when it's new. So we have to try to keep that mirror clean, and we do that through two different methods. One is that we do approximately a monthly, what we call snow cleaning. Snow cleaning is using frozen carbon dioxide to bombard the surface. You can think of them as little ice chunks bombarding the surface of the mirror to release any dust that's adhered to the front of the primary mirror. You can imagine we have to operate every night of the year, and we open up the dome, and there is dust, and there is wind, and there are moths, and there are birds and whatnot that can potentially degrade the primary mirror, and so we need to try to keep it clean. So the process we use is we use the snow cleaning, but then twice a year we do a contact wash, and that's really what this picture is showing here, is that process of washing the primary mirror. We start off by flowing water over the primary mirror, and then we use a very mild detergent with these custom soft mops here, and we dab the surface of the mirror. We go around and dab the surface of the mirror to get it clean. And we don't want to drag those across the surface because there are any dust particles. There are any dust particles left on the mirror. We can drag them across the aluminum and it can scratch the aluminum. We don't want that. So we just dab the mirror to keep it clean. And you might ask the question, like you can see these guys, they got harnesses on, standing on the outside of this cell here. But you know, this is 6.5 meters in diameter, so it's kind of tough to reach this area in here. So what we do is we actually have a separate mop. You can see there's ropes up here that go up to the secondary and hold one mop that allows us to dab around the central hole right there. Next slide. But, oh, yeah, so this is our software engineer's creative, and he said, hey, why don't I just do this? We don't do that. Yeah, I think they're going great. Okay, next slide. But despite all our efforts to keep the primary mirror clean, we do need to strip off that aluminum every few years. We nominally do it every 5 years. Take that aluminum off because it's degraded enough and put a new coating of aluminum on the surface. So I'm going to describe to you how we do that over the next few slides. It's a pretty quick process. You can see here that, actually it's not a quick process to strip the old aluminum off. You can see here, there's an image of the primary mirror. You can see it's reflective, so there's aluminum on it. And the day that this was done, I went up and I took a picture, and then I had a telecom that I had to attend for about an hour. And when I came back, next slide, this is what it looked like. So we had stripped the aluminum off the mirror. That was in less than an hour time. We had stripped it off. We use a combination of an acid and a base. The acid helps strip the aluminum off, and then the base neutralizes it to keep us from etching the glass underneath it. So this is the process after they finish stripping the mirror. Then we go through a process of getting it very, very clean. Next slide. We wash the mirror, and then we have to go through and we have to dry it. We don't want to leave any water spots on the thing. So we do that in this very complex mechanism of using chem wipes, throw it all over the surface of the mirror, and a couple of people getting down on the mirror in their bunny suits. Next slide. And then they go around and they dab the mirror to get all the water off of it. Next slide. And they continue around. Next. 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 This is better when I'm not saying next. So after the mirror is all clean, then it looks like this. This is the nice pristine mirror without any aluminum on the surface of it. Next slide. And here's a picture of me that day standing in front of the mirror. I want to get a picture there because we don't often see the telescope without any aluminum on the primary mirror. In fact, this close-up of the those hex cores in the mirror, actually, you can see that there's wording in them. So there's multiple different hex cores that have things in them. Here is the seal for the University of Arizona. And here is the seal for the Smithsonian Astrophysical Observatory. I guess I meant to say in my opening slide, I had the symbol for both Arizona and Smithsonian. MMT is a partnership between the University of Arizona and the Smithsonian Astrophysical Observatory. Each of them contribute 50% of the operating costs for the observatory. That's why both of them are here, University of Arizona and Smithsonian. And then the NSF, there was some funding to make the mirror by the NSF, and then the mirror lab is in this hex core up here. Next slide. Just a few more slides here showing you the process of actually illuminizing. This is the telescope pointing over at horizon here. So this is the back of the telescope. We're now pointing at horizon, actually pointing Mount Wrightson over there. The telescope structure, which holds up those secondary mirrors, is right here. We actually have to take some of that apart in order to do this process. So this is what the guys up here are doing. They're taking the hardware out, and we've got this part of the structure up on a crane, and we're going to lift it out of there. Next slide. And there it is being lifted out, the front part of the telescope structure there with the crane. Next. The next thing we need to do is we need to create a vacuum bell jar. So in order to deposit aluminum onto a mirror, we need it in a vacuum so that we can heat up the aluminum, vaporize it, and have it travel to the mirror without getting obstructed by any air or anything in between. In the MMT, you saw the footprint of the summit. It's very small there. Typically, what you would do is you would build a coating chamber right there next to the telescope, and you bring the telescope, you take the mirror out of the telescope and bring it into the coating chamber to coat it. Well, there wasn't enough room to do that at the summit of Mount Hopkins, so the decision was made, we'll just use the telescope itself. We'll leave the mirror in there, and then we'll just put a big steel structure over the mirror to create this vacuum bell jar we need for depositing aluminum. So this is a picture. You can see the long road up here. Here's the ridge out here. This is a picture of that big steel structure that's going to go in front of the mirror for doing the illumination, coming up the very last deep section of the road. Next. And this is the inside of that structure. So you saw the back side, now you're seeing the front side. What you can see is there's 3 concentric rings internal to this. This is the second, this is the third here. So 1, 2, 3 rings. And on those rings, you can see there's individual things there. Those individual things are what are called filaments. Here's an image of a filament. They're very similar to the filaments from incandescent light bulbs. You know, you look inside a light bulb and you see the coiled up filament. In fact, they're made of the same thing. They're made of tungsten. But these are much bigger. They're a couple, maybe 6 inches across or so, coiled up. So they're tungsten filaments, but stranded in there with one of the strands of tungsten is pure aluminum. And what we do is we heat up these tungsten filaments to the point where the aluminum melts and vaporizes and then coats the surface of the primary mirror. So you can see there's 200 of them in this bell jar here, and we're about to hook up a bank of big welders in order to put enough current through there to heat up that tungsten and melt the aluminum. Next. Here's an image of that bell jar being lifted into the telescope. It's going to go right in front of the telescope and get bolted to the front of the telescope there. Next. And it's a pretty tight fit. Just fits in between the telescope structure and the primary mirror there. And this is showing that bell jar now right in front of the primary mirror. Next. And just before we close it up and bolt it up and start the process, this is looking down now from the top. You can see on the bottom here is the primary mirror. No aluminum on it. We have a mylar barrier here, which separates the vacuum on the front side from the back side. Here's some people prepping some things. And then over here on the top, you can see that that's the actual bell jar. You can see these rings right here, here, and the outer one that have those 200 filaments. So this is just about to close up and start that process. Next. And This is going to show a video of that process actually happening. You can hit again, Steve. Here we go. So we're looking into a port into this bell jar. This is all in a vacuum now. We now turned up the welders to heat up those those tungsten filaments. And what you can see is that individual filaments, you're seeing them in reflection from the glass mirror. You can see the honeycomb structure there. As the aluminum begins to melt and coat the surface of the mirror, no longer do you see that honeycomb structure. You're just seeing the aluminum, and now you see a better reflection of those individual filaments there, heating up and coating the surface with aluminum. Next. And now you can see we're turning it down. So here's another image of that, those filaments heating up. The amount of aluminum we deposit on the surface of the mirror is only about 2/3 of an aluminum can. So it's a very, very thin layer, 1,000 angstroms of aluminum on the surface of that big 6.5 meter mirror. Next. And if everything goes well, you take that bell jar out and you look into the primary mirror, and it's nice and reflective like this. So this is showing us looking into the primary mirror. The person taking the picture is up on this lift here, looking right into the primary mirror. The mirror is pointed back toward Mount Wrightson, and you can take a picture of yourself. Next. And I guess that's it. Thank you so much. Sorry about the
Need lights.